Now, this is a very sad story. So this bird is called passenger pigeon, and 200 years ago, this species was abundant in America. You know, they lived in huge flocks, and it was considered a source of cheap food, and it was hunted for food. And there were so many of them then that no one could think that they could disappear. And yet, that's exactly what happened. Well, so when they were being hunted for food, at some point, people realized that okay, maybe we should stop, because you know, the population of passenger pigeon disappears, and people stopped. And but at the same time, there were still a lot of birds alive, still huge flock of birds lived. But what happened is that they stopped reproducing, and the hypothesis here, so that this was a very social species. So in order for them to feel happy, and in order for them to reproduce and to survive as a species, they had to live in huge populations. And if a particular population drops below a certain threshold, well, because of some reason, then they would disappear, because they would stop reproducing. And although the overall number of specimen of birds was still sufficient to probably sustain and to survive and to recover the population, but every particular flock happened to be below that threshold, which is why, sadly, all the individual colonies of these birds, they went extinct, and the whole species is now extinct. Okay. So now how can we model this? So what we need is basically the idea here. Let me try to explain. So if this is the plane T, Y, then what we should have is not two, like in the logistic equation, but three equilibrium solutions. So one of them is 0, right? So 0 should be an equilibrium solution. So then another solution is called T, threshold. So y equals T is an equilibrium solution. And then y equals K is also an equilibrium solution. That's the carrying capacity. Then y equals K should be a stable equilibrium. So above y equals K, all the arrows, they point downwards, and below it, all the arrow point upwards, so that all solutions converge to K exactly. But then not below T, because below T, what we are going to have is below T, all arrows also point downwards, and then which tells us that if the initial population is below T, then it's going to decline, and the limit is going to be 0. Well, and then if you think about it, then as the right-hand side of the differential equation, you need a function such that its zeros are 0, T, and K. So let me try to plot it here. So if we want to this horizontal axis is y, so we need a function such that it is 0 at 0, then at T and K, then more than T is negative, here positive, here negative and positive. So positive, negative, positive, negative. And then the simplest that you can do is a cubic polynomial, and that's what it is. So this is called the logistic equation with a threshold. Okay, so now if we have the logistic equation with a threshold, then we have not 2 but 3 equilibrium solutions. So stable equilibrium y equals 0, which is the same as the usual logistic equation, and unstable equilibrium y equals t, which is the threshold, and then another stable equilibrium y equals k. That's the carrying capacity. And this is a sample of solutions. Right? So if the initial point is slightly above the threshold, then the population is going to grow and eventually is going to approach the carrying capacity. If the initial population drops slightly below the threshold, then it's going to converge to 0. And this is what's been conjectured to have happened to the passenger pigeon. So because of hunting, every individual colony, in every colony, the initial population dropped below the threshold and they disappeared. Okay, so